Okay, so here we're going to talk about simplifying radicals. Now, before we can talk about that, let's just talk about what a perfect square is. So, I mean, you could read it right here. A perfect square is the square of a whole number. So if I take 1 and square it, 1 squared is 1. Let's just make a little list here. 2 squared would be 4. 3 squared is 9. 4 squared, 4 times 4 is 16. 5 squared is 25, and this list keeps going. So I'm just going to fit whatever I can on here. So let's see, we have 36, 49, 64, and I'm just going to write ... Okay, the list just keeps going. Okay, now, these are examples of numbers that are perfect squares. You could also have perfect square variables. So if I said to you, what is x times x? Well, x times x is x squared. If I said to you, what is x squared times x squared? So in other words, what's x squared squared? It would be x to the 4th. If I said to you, what is x cubed squared? So for example, I'm going to write this one out. If I said to you, what is x cubed squared? Well, remember, when we have a power raised to another power, we multiply these. So I'm going to put x to the 6 on our list. Okay, so continuing with that trend, if I said to you, what is x to the 4th squared? Again, when we have a power raised to another power, we multiply these. So that'll give us x to the 8th. All right, keep going. What is x to the 5th squared? That'll give us x to the 10th. And if you notice the pattern going on here, I mean, basically, any even exponent is going to be a perfect square. So if I wanted to put the next, it would be x to the 12th, and then x to the 14th, and so on. So for any of these variables with the exponents on it, if I wanted to take the square root of it, so for example, let's just take a look at this one right here, x to the 10th. If I wanted to take the square root of x to the 10th, all I have to do is take this exponent and divide it by 2. Just cut it in half. So the square root of x to the 10th would be x to the 5th. And again, the reason for that is because x to the 5th, when you square it, is going to give you x to the 10th. Okay, so I know I already said this, but I just want to write down that basically your variables here are perfect squares as long as they have even exponents. So in other words, the exponents are divisible by 2. Okay, they divide evenly by 2. All right, well, let's take a look at some examples where we're going to have to simplify radicals. Now, if you look at number 1, all right, 75 and x to the 9th, those are not perfect squares. Those are not on the list that we just made. So what you're going to want to do is you're going to want to take this and break it up into 2 separate square roots. And what we're going to do is we're going to put all of our perfect squares under this first radical, and what we're left over with, all of our non-perfect squares, under the second radical. So if you look at a 75, what you want to do is you want to say, well, what's the biggest perfect square that divides evenly into 75? Well, 25 is. So I'm going to take 25 and put it in my perfect square radical. And since 75 divided by 25 is 3, 3 is what goes as our leftover in the non-perfect square radical. Now, x to the 9th, even though 9 is a perfect square, okay, we're not looking at a number. We're looking at a variable raised to a power. And remember, we said that in order for it to be a perfect square, it has to have an even exponent, which this isn't. So what you want to do is you want to take out the biggest perfect square that you can out of x to the 9th. So the biggest perfect square that you can pull out of an x to the 9th would be x to the 8th. And that would leave you with 1x left over to put into our perfect square radical. Okay, so now let's just simplify. So the square root of 25 is 5. And the square root of x to the 8th, remember, you just take the exponent and divide it by 2. So it would be x to the 4th. And then whatever's in this radical, nothing is going to simplify because we've already taken out as much as we can out of the radical. So you're just going to take that and bring it right down. So there's our answer. Okay, let's take a look at number 3. Let's do it again. So now as we look at number 3, you can see there's some things under here that are perfect squares, but not everything is. So we're, again, going to break this up into 2 separate radicals, our perfect square radical and our leftovers, our non-perfect square radical. Okay, so if you want to look at the number 48, now there are a few different perfect squares that divide evenly into it. So for example, 4 is a perfect square. 4 times 12 would give you 48. But we want to find the biggest perfect square that divides evenly into 48. So the biggest perfect square that divides evenly into 48 is 16. And since 48 divided by 16 is 3, we're going to put our 3 in the leftover, the non-perfect square radical. All right, so now if we look at x to the 5th, this is an odd exponent, so it's not a perfect square, but the biggest perfect square that we could pull out of there is x to the 4th, leaving us with an x left over here. Our y to the 4th and our z squared, those both are even exponents, so we can put those entire terms into our perfect square radical. So we're going to have y to the 4th and z squared. There's not going to be any left over in our non-perfect square radical because these are perfect squares. Okay, so the square root of 16 is 4. The square root of x to the 4th is x squared. Remember, you divide the exponent by 2. The square root of y to the 4th is y squared, and the square root of z squared is just c. And from here we can bring down our radical 3x, what's left over. So there's our answer. Okay, and the last one we're going to take a look at is number 5. This negative 4 in front, we're just going to take and bring right down. And since not everything in here is a perfect square, we're going to take it and break it up into 2 separate radicals. Okay, just like the last problem, I mean, there's more than one perfect square that divides evenly into 32, like 4 and 8. We could break that up in 2, but it's not the biggest perfect square. The biggest perfect square that divides evenly into 32 is 16. So I'm going to put a 16 here, and since 32 divided by 16 is 2, we'll put the remaining 2 over here. All right, x to the 7th, we have an odd exponent, so it's not a perfect square. The biggest perfect square that you could pull out of that is x to the 6th, and that would leave us with 1x remaining in our leftover radical. All right, y to the 8th, that is a perfect square because 8 is an even exponent, so I'm going to put the whole thing right here. Z to the 15th is not a perfect square because 15 is an odd number. So the biggest perfect square you could pull out of z to the 15th would be z to the 14th. And that leaves us with a z in our non-perfect square radical. Okay, so what I'm going to do is I'm going to bring this negative 4 down, and I'm going to open up a parenthesis, because what we're really doing here is negative 4 times this radical. So let's break down that radical. The square root of 16 is 4. The square root of x to the 6th would be x cubed, right, because we divide the exponent by 2. The square root of y to the 8th would be y to the 4th, and the square root of z to the 14th would be z to the 7th. And I can bring down the rad 2xc. Now, even though this 4 right here, even though this is a perfect square, I don't want you to say, oh, the square root of 4 is 2, so let me bring down a 2, because this 4 is no longer under a radical, so don't try to take the square root of it again. But what we are going to do is we're going to multiply this negative 4 on the outside of the parentheses. We're going to distribute it into the parentheses. So negative 4 times 4 is negative 16. So we're left with negative 16 x cubed y to the 4th z to the 7th, and then you can bring down the radical 2xz. Okay, so if you turn to the back of the page, just turn to page 2, here we're going to talk about perfect cubes and then perfect fourths as well. All right, so a perfect cube is just really the cube of a whole number. So if you take 1 and cube it, 1 cubed, 1 times 1 times 1 is 1. So I'm going to put that first on our list here. 2 cubed, 2 times 2 times 2 is 8. 3 cubed, 3 times 3 times 3 is 27, and so on. So I'm just going to list a few of these out. So 4 cubed is 64, 5 cubed is 125, 6 cubed is 216, and the list will just keep going. So I'm just going to write ... All right, now let's talk about variables. If we take an x and cube it, we would write that as x cubed. Okay, now if we took, let's say, an x squared and cubed it, Well, when we have a power being raised to another power, we could just multiply these. So this will be x to the 6th power. All right, so now let's take x cubed and cube it. So again, when you have a power to power, you just multiply these, so that'll give you x to the 9th. If we take x to the 4th and cube it, that'll give us x to the 12th. So x to the 5th cube would be x to the 15th, and so on. Our list keeps going, so I'm just going to put ... Okay, so what you should notice about all of these exponents is they're all multiples of 3. Or another way of saying that is they're divisible by 3. So I'm going to write that out. So I'm just going to say the exponent is divisible by 3. Okay, just like a perfect square, the exponent is divisible by 2. Okay, so what we're going to do is if you take a look at number 7, we're going to simplify that. We're going to do it really the same way we simplify perfect squares. All right, so first thing you want to do is you want to look at what's under the radical. And if everything under here is not a perfect cube, we want to take this and separate it into 2 separate radicals, where the first radical is going to contain all of our perfect cubes, and the second radical is going to contain all the leftover terms. All right, so if we take 24, let's look at that and say, well, is that a perfect cube? If we look on our list up here, 24 is not on our list. So we want to say, well, what's the biggest perfect cube that divides evenly into 24? Well, 8 is. So I'm going to put 8 in our perfect cube radical. And then since 8 times 3 gives us 24, I'm going to put that leftover 3 right here. All right, so now let's look at our 8 to the 6th. If we look at the exponent, 6, that is a multiple of 3. That is divisible by 3. So 8 to the 6th is a perfect cube. So I'm going to take that and put the whole entire thing in our perfect cube radical. All right, now if we look at the b to the 10th, 10 is not divisible by 3. So b to the 10th is not a perfect cube. So we want to look at this and say, well, what's the biggest perfect cube, or what's the biggest multiple of 3, that we can pull out of a b to the 10th? So that's the biggest, multiple of 3 that's less than 10 would be 9, so we can pull out a b to the 9th. b to the 9th is a perfect cube, and that's going to leave us with just one b left over to put here. All right, so now let's just simplify our first radical. So the cube root of 8 would just be 2, because 2 times 2 times 2 gives you 8. The cube root of 8 to the 6th would be a to the 2nd, because a to the 2nd times itself gives you a to the 6th. A shortcut way, there's a rule, we say power divided by root. If you take your power and divide it by the root, that'll give you our exponent right here. So if we do this again, if we have b to the 9th, if we want to take the cube root of b to the 9th, we can write b, and then we'll do power divided by root. So 9 divided by 3 is 3, so that'll give us b cubed. And then you're just going to bring down the leftover radical. So this would be the answer for number 7. All right, so let's talk about perfect fourths, and it's really just going to follow kind of the same trend of everything we've been doing with perfect squares and perfect cubes. All right, so if we want to list out our numerical perfect fourths, let's see, 1 to the 4th, 1 times 1 times 1 times 1 is 1. 2 to the 4th, 2 times 2 times 2 times 2 is 16. 3 to the 4th is 81. 4 to the 4th is 256. And I guess I'll just do one more. 5 to the 4th power is 625. So it's a good idea to just kind of make a list of these first. All right, so now we knew that with variables, in order for it to be a perfect square, the exponent had to be a multiple of 2. In order for it to be a perfect cube, the exponent would have to be a multiple of 3. So in order for it to be a perfect fourth, the exponent would have to be a multiple of 4. So our first perfect fourth variable term would be x to the 4th. Okay, the next one, if you took x squared and raised it to the 4th power, it would give you x to the 8th. The next one, if you took x cubed and raised it to the 3rd power, it would give you x to the 12th. So you'll just see, you could see the trend. Our exponents here are just all the multiples of 4. And that list just keeps going and going, so we'll just put put a dot, dot, dot. So if you just want to put a note here, just kind of like we did for the other ones, the exponents are divisible by 4. And we're not going to actually, do any more than this, but if you did perfect fifths, the exponents would be divisible by 5. Perfect sixths, the exponents would be divisible by 6, and so on. All right, so let's take a look at number 9 together. Now, if you look at the number right here, 162, that is not on our list. So what we're going to do is we're going to take our radical, and we're going to break it up into 2 separate radicals. All right, so you want to say, well, what's the biggest number that divides evenly into 162? That's on our list, so that's going to be 81. 81 times 2 gives us 162. So I'll put the 81 in the perfect fourth radical and the leftover 2 in the other radical. All right, so if we look at x to the fifth, well, 5 is not a multiple of 4. So what we're going to do is we're going to take out the biggest perfect fourth that we can. So the biggest perfect fourth that we could take out of this would be x to the fourth. And that would leave me with just an x in our leftover radical. All right, y to the 12th. This is a perfect fourth because 12 is a multiple of 4. So I'm going to take the whole thing and put it in our perfect fourth radical. All right, so then the fourth root of 81 is 3. And if you didn't know that, you could go in your calculator. If you hit math and scroll down until you see the xth root, so that would be choice 5, you could plug in, you could basically substitute that x with a 4, and you could plug in the fourth root of 81. All right, but anyway, the fourth root of 81 is 3. The fourth root of x to the fourth is just x to the first power, right? So we can write that as x. Again, 4 divided by 1 is 1. And then the fourth root of y to the 12th would be y cubed, because if you divide the exponents, right, take the power and divide it by the root, 12 divided by 4 is 3. And then you would just bring down your leftover radical. Okay, so for homework tonight, you guys are going to go back and do all the even questions that we skipped on this. So 2, 4, 6, 8, and 10. You're also going to go on to the next 2 pages, which is operations with radicals, and I'm going to do the odds with you again, and then you guys can do the evens as well for homework. Okay, so if you turn to page 3, operations with radicals, let's take a look at number 1. Now, in order to add radicals, you have to have the same number under the radical. So you can't just say, oh, look, radical 72 plus radical 18 is radical 90. You're not allowed to add these if they have different numbers under the radical. So what you want to do is you first want to simplify your radicals. So since 72 is not a perfect square, I'm going to break that up into radical 36 and radical 2. And then the square root of 36 is just 6, so I'll rewrite that as 6 radical 2. Okay, now 18 is also not a perfect square, so I'm going to take that and break it up into 2 separate radicals. And the biggest perfect square that divides evenly into 18 would be 9, so I'll break that up into radical 9 and radical 2. So we can rewrite that as 3 radical 2. Okay, so again, the first thing we did was we just simplified our radicals. Now, if you look here, here we have a radical 2, and here we also have a radical 2. So as long as the radicals say the same exact thing underneath them, you can just take these numbers in the front and add them. So when we add these, we would get 9 radical 2. And I just want to point out, if you did wind up with something different under your radicals, like let's say we wound up with 6 radical 2 plus 3, let's say instead like radical 5, well, since these do not say the same thing under the radical, this would just be your answer. Okay, you can't combine them, so this would be your answer. Okay, but that's not the case, so let's just kind of erase that to get that out of there. All right, so if you take a look at number 3, now you could see this does not say the same exact thing as this underneath the radical. So let's just go through and let's simplify our radicals. All right, I'm going to start with this first term right here. So let me bring down first what's in front of the radical. So I'll bring down the 9x squared and the y cubed. And then I'm going to take this radical x to the 25th y and break it up into 2 separate radicals. All right, so you want to first look at the x to the 25th and say, is this a perfect square? Now, even though 25 is a perfect square, x to the 25th isn't, because in order for it to be a perfect square, the exponent has to be divisible by 2, and that's not. So the biggest perfect square that I could pull out of this would be x to the 24th. And that would leave me with just an x in my leftover radical. All right, now if you look at the y is not a perfect square, and there's really no perfect square you could pull out of that, so I'm just going to bring that y down to my leftover radical. So let's see, right now we have 9x squared y to the third. Now the square root of 24, you just take the exponent and divide it by the root, which is a 2. So 24 divided by 2 is 12. So that's going to become x to the 12th. So I'm just going to write times x to the 12th, and I'll bring down my radical xy. Now here we want to multiply these together. So if you multiply x squared by x to the 12th, when you multiply two terms with the same base, we add the exponents. So that's going to give us 9 x to the 14th y cubed, and we can bring down that radical xy. Okay, now let's go through and simplify the next one. So let me bring the x squared down, and I'm going to break this up into two separate radicals. All right, let's start with the 9. Well, 9 is a perfect square, so I'm just going to take that whole thing and just put it in our perfect square radical. X to the 25th, just like we saw before, it's not a perfect square, so we could take out x to the 24th, and that would leave us with an x in our non-perfect square radical. And then y to the 7th, 7 is not divisible by 2, so the biggest perfect square that you could take out of y to the 7th would be y to the 6th, and that would leave me with just a y in my leftover radical. Okay, so I'm going to bring down my minus x squared, and the square root of, basically everything in this radical right here is going to leave us with, I'm just going to put a parenthesis to multiply this time, 3 times x to the 12th, and then times y to the third. Remember, you just take that exponent and divide it by the root, so when you divide it by 2, it gives you 3, so you get y to the third. And I'll bring down my radical xy. All right, so now we're going to multiply these, and basically the same thing, x squared times x to the 12th, you add the exponent, so it gives you x to the 14th. So we'll have minus 3 x to the 14th y cubed radical xy. Okay, so now we want to look and say, are these like terms? Can we combine them? Well, in order to be able to combine them, not only do you have to have the same thing underneath the radicals, which we do, but you also have to have the same exponents on these variables in front. So like this says x to the 14th y cubed, so does this over here, x to the 14th y cubed. So these are like terms, so we can combine them. So since 9 minus 3 is 6, I actually can't fit this on my screen, so I'm going to just kind of take this and bring our answer up here. Sorry to do that. But again, since 9 minus 3 is 6, I'm going to be left with 6, and then just kind of attach everything to it. X to the 14th, y cubed, radical x, y. Okay, and now in number 5, instead of dealing with square roots, we're dealing with fourth roots. Now, I know you could flip back in your packet and just kind of look at the list of the perfect fourths that we listed out, but if you were taking a test, you wouldn't have that list in front of you. So it kind of is a good idea to start these by just writing out a list of all your perfect fourths. So like, I'm just going to make a short little list. So 1 to the 4th is 1, 2 to the 4th is 16, 3 to the 4th is 81, 4 to the 4th is 256. And I'm actually going to stop there because if you look at the numbers we're working with, nothing is higher than 256 anyway. All right. If we want to make a quick list, you kind of don't have to do it with the variable exponents. We know that if the exponent is a multiple of 4, it is a perfect fourth. All right, so let's go through and let's simplify these first and try to get the same thing under the radicals if we can. And then if so, we'll combine them. And if we can't get the same thing under the radicals, if we can't get like terms, then we just don't combine them. All right, so what we're going to do is we're going to break this up into two separate fourth roots. Okay, so 32 is not on our list over here of perfect fourths, but 16 is, and 16 divides evenly into 32. So I'm going to break the 32 up into a 16 under our perfect fourth radical and a 2 in the leftover radical. All All right, x to the 12th is a perfect fourth because 12 is divisible by 4. So I'm going to take that entire thing and put it in our perfect fourth radical. Okay, so the fourth root of 16 is 2, and the fourth root of x to the 12th, just do power divided by root, so 12 divided by 4 is 3, so it'll give us x cubed. And I'll bring down my fourth root of 2. Okay, let's bring down my minus sign, and let's work with the next one. All right, so let me first bring down the 2x cubed, and let's break up the fourth root of 162 into two separate radicals because 162 is not on our list of perfect fourths. But we could see 81 is, and 81 times 2 gives us 162. So I'll put the 81 in our perfect fourth radical and the leftover 2 in the other radical. All right, so let me bring down the 2x cubed, and the fourth root of 81 is just 3. So we're going to write times 3, and I'll bring this down. Okay, so we have right now 2x cubed times the fourth root of 2, and then minus, well, when I multiply 3 times 2x cubed, it's going to give me 6x cubed. And that's going to be times the fourth root of 2. And just one thing I want to point out, when you write these, don't forget to put the little 4 in there, because if not, it means the square root. All right, well, we have fourth root of 2, and these both have an x cubed on it, so they are like terms. So 2 minus 6 is negative 4, so this will leave us with negative 4x cubed times the fourth root of 2. All right, so if you can turn to number 7. On the back of this page, we're going to be dealing with multiplying and dividing radicals. So number 7 is multiplying radicals. So the steps for multiplying radicals are right here. So step number 1 says to multiply the terms outside the radical. So we have a negative 4 times 3. So that would just be negative 12. Okay, step 2 says to multiply the terms under the radical. So I'm going to take the 12x to the 7th and multiply it by 2x. And when I multiply them up, I'm going to put them under a radical. All right, so 12 times 2 is 24. And x to the 7th times x to the 1st, just add the exponents, would be x to the 8th. All right, and then step 3 is to simplify. All right, so let me bring down the negative 12, and I'm going to break up this square root into two separate square roots. And since 24 is not a perfect square, the biggest perfect square that I could pull out of 24 would be a 4, so I'll put a 4 in my perfect square radical, and a 6 in the leftover radical. And then x to the 8th is a perfect square because this exponent is even. It's divisible by 2. So I'm going to put the whole entire thing in my perfect square radical. All right, so let's bring down the negative 12. The square root of 4 is 2. And the square root of x to the 8th is x to the 4th. Just take the exponent and divide it by 2. And let's bring down the radical 6. So now we multiply what's on the outside over here of these radicals. We have negative 12 times 2x to the 4th. So that'll be negative 24 x to the 4th. And I'll bring down my radical 6. All right, number 9, it also deals with multiplying, but here we're multiplying a binomial, right, 2 terms, times another binomial. So we know whenever that happens, we're going to double distribute. So I'm first going to distribute the 4 to both terms. So 4 times 2 is 8, and 4 times 7 radical 5. Well, all we're really going to do is just multiply the numbers on the outside of the radicals. So 4 times 7 is positive 28, and I'll just bring down the radical 5. Okay, then negative 3 radical 5 times 2 would be negative 6 radical 5. So I'll write minus 6 radical 5. And then negative 3 radical 5 times positive 7 radical 5. Well, let's follow the rules for multiplying radicals. Multiply the terms on the outside, so negative 3 times 7 would be negative 21. And then we're going to multiply the terms underneath the radicals and we'll put them under a radical. Well, 5 times 5 is 25, so we could put radical 25. But radical 25 is just going to simplify to 5, so you can cross that off and make it a 5. So a little shortcut, rather than writing radical 5 times radical 5 is radical 25 and canceling it off to make a 5, a radical times a radical of itself, of the same, term underneath, is always equal to just that term. So if I said, what is radical 8 times radical 8? It's just 8. Radical x times radical x is just x. Radical 1,000 times a radical 1,000 is just 1,000. So if you want to just skip to just, for this, instead of writing radical 25, you could just make it a 5. All right, so then I guess what we could do is we could just multiply the 21 times 5, which is 105. So I'm going to make this a minus 105. And I guess I'll just bring everything else down for now. And from here, we'll combine our like terms. So I'm going to first combine my numbers. We have 8 minus 105, which is negative 97. And then the 28 rad 5 and the negative 6 rad 5 are like terms because they both have a rad 5. So that'll give me positive 22 radical 5. All right, and the last one I'm going to do with you guys in this video is number 11. And it's just dividing radicals. Now, the steps for dividing radicals are really the same exact steps as we did with multiplying radicals, just change the word multiply to divide. So we're first going to divide the terms outside the radical. So we have a 2 divided by 10. So that's really just going to simplify to 1/5 for us. So I'll rewrite that. I'll just do it over here as 1/5. Now, when we divide what's under this radical by what's under the radical in the denominator, we're just going to put it under one single radical. So let me put a radical, and then 500 divided by 5 would be 100. X to the 12th divided by x to the 1st, you just subtract the exponent. So 12 minus 1 is 11, so that would give me x to the 11th. And then y to the 7th divided by y, again, just subtract the exponents, would give you y to the 6th. And then we're just going to simplify our radical. So let me bring down my 1/5. I'm going to break this up into 2 separate radicals. Now 100 is a perfect square, so I'm going to put the whole thing under our perfect square radical. X to the 11th is not, because we have an odd exponent, so it's not divisible by 2. So the biggest perfect square that I could pull out of there would be x to the 10th, leaving me with an x over in my non-perfect square radical. And then y to the 6th is a perfect square because its exponent is divisible by 2. All right, so let me bring down the 1/5, and then the square root of 100 is 10. The square root of x to the 10th is x to the 5th, because we just divide the exponent by 2. And the square root of y to the 6th is y cubed. And I'll bring down my radical x. So that when you multiply, 1/5 times 10 is 2, so we'll have 2 x to the 5th, y cubed, radical x. All right, so now what I want you to do is I want you to go back and I want you to try, throughout pages 1 through 4, just all of the even examples. And then the next time I see you guys, we will go over those together.